Okay, this is AQA 2020 paper 3 part A, the practical skill section. Now, as per usual, I can't show the paper on the screen because unlike the other boards, AQA will have my channel deleted like they almost did in the past. But links to the paper and the mark scheme are below for you to have a look. Question 1, we're being asked about a practical involving a pendulum. 1.1, we have a card as a fiducial marker. Where would we put the marker? Now, this has caused some controversy with my lot anyway. We had a good long chat about this. Now, personally, I would have the card behind there, just right at the bottom there, because you can see when the string passes the line through the middle. But AQA, in their infinite wisdom, say, no, that's not good enough. It needs to be below the bob. And not only that, they say, actually, do you know what's even better? Is if the mark on the card is at the edge of the bob when it's hanging straight. It's ridiculous, isn't it? Absolutely ridiculous. Because as if a bob is swinging and you can actually tell the difference between whether the middle of the bob is in line with the line or whether it's the end of the bob. It's ridiculous. I mean, if we use a slow-mo camera and that kind of thing, sure, we could do that. But if we're just timing it, then it's just ridiculous. So they say have it below the bob. I don't know. This is classic AQA. Not off to a good start, AQA. Let's try again. 1.2. So we have our bob is going to be there, and then it's going to be at a maximum here. So we need to be able to measure this distance here. And we have the floor as well. So whenever it comes to any measuring of something which is off the floor or off a ruler, then the best thing to do is have a ruler on the floor, flat, but then we like to have a set square then, don't we? And so we should have a set square that we put there. We should put it really against the edge of the bob, because having it in the middle, well, we're not going to be able to tell. And if we have it there as well at the edge, then actually this distance here is going to be the same as that distance there. So the answer is using a set square and ruler to measure distance between edge of bob at equilibrium and amplitude. There you go. 1.3, we have this graph, and we have time on the y-axis, and we have AR on the x-axis. And we have this line that goes up here, but then we're being asked to estimate what happens when AR increases from the 0.35 to 0.7. So therefore, 0.35 is down here. So yes, we're having to extrapolate our little line here up to here, so there is going to be some ambiguity there. So I get that to be 2.319, and I reckon once I've extrapolated my little line here, I think that's about something like 2.356, I'd say. So therefore we're looking for a percentage change. Any percentage is the bit divided by the lot, so that's going to be equal to our difference in values. So 2.356 take away 2.319 divided by our original value, and then of course times by 100. And that gives me, well, to 3 sig figs, 1.60%. Mark scheme says anywhere between 1.4% and 1.8% is acceptable. So therefore we're okay. They say their value is 1.5%, and if that's the case, then we end up with 2.354, but I think that's far too low. Because that would, that doesn't make any sense. 1.4, we're being asked to find a mean, but we've been given 6 values, and so let's see if we have an anomaly. 0.247 looks like it's a bit of an anomaly, so we're going to omit it from our calculation. So we're just going to use the rest of the numbers, divide that by 5, and we end up 2. We've got to make sure that our mean is the same level of accuracy, so 0.221. Now, what's funny is that the mark scheme says that if you don't omit the anomaly and you just use all 6 values, then you'll get full marks. Now I can say that's the very first time I've ever seen that in a paper. It's always been the case in the past that if you do not omit the anomaly, then you'll get docked a mark. So I'm going to say always look for an anomaly and then omit it from the calculation. Okay, percentage uncertainty in mean. Well, actually, I tell you what, we're just going to say, first of all, the absolute uncertainty in the mean. So just the uncertainty. It's half the range. So it's going to be our biggest value. So it's going to be our biggest value, 0.225. Take away our smallest value, 0.217. And that gives us 0.004. So then we want percentage uncertainty. Any percentage uncertainty is the absolute uncertainty divided by the value times 100. So therefore, that's going to be our 0.004 divided by our value of 0.221. Actually, I can just say that's 400 divided by 221. And I can see that gives me 1.81%. Easy. 1.5, we have a table involving natural log. Oh, love a bit of natural log. So first of all, we're just being asked to complete the table. Easy. So the natural log of 0.225, that gives us minus 1.492. Okay, so then we're being asked to plot the graph. Okay, that's fairly easy. You guys know how to do that. We are going to end up with a negative gradient graph. Okay, we're being asked to explain how we would find delta from our graph. So here's our equation. AN equals A0 delta to the minus n. So we have an equation that has an unknown power. If we have an unknown power, we know we have to use logs. In this case, they've already told us that they want us to use natural logs, but we could use log base 10 if we wanted to, if they didn't tell us that. So we need to use our log identity. So first of all, let's just log both sides. There we go. Now let's split up what's inside the log on the right hand side. So the log of two things multiplied together is equal to those two logs added up. And finally, we just want to get the unknown power out. So log of AN is equal to log of, I'm going to do that the other way around. Say minus the log of delta. Yeah, let's say that. Minus the log of delta. That's times, of course, plus the log of A0. Okay, so I've done it that way around because, of course, we have our y here and our x here. So if we do y equals mx plus c, this is actually our m because this is our x, isn't it? So therefore that means that, well, we don't really care about that because we're being asked about delta, aren't we? So therefore, we can say that the gradient is equal to minus the log of delta. So I guess we could say minus the gradient is equal to the log of delta. But we're not done because we're looking for delta itself. So therefore, we need to delog this equation. The opposite of natural log is e, of course. So we can say that, I'm just going to say delta is equal to e to the power of minus the gradient. So just going to know your log identities and know how to apply that to a straight line graph and figure out what's going on. 2.1, we have this vernier scale. We have this distance between our supports. Okay, first things first, we're being asked what is the reading on the vernier scale? Well, of course, we can see that it's going to 30, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And we can see that the 0 is going past, well, that's 35, so 36, 37. So therefore, it's going to be 37 point something. Oh, okay. Well, the only answer could be 37.8, but let's just check the 0.8. Yes, it is the 1, 2, 3, 4, 5, 6, 7, 8. That lines up with a line best on the bottom scale. So that is our answer. 2.2. We're now hanging a mass off here. Okay. The vertical deflection S is equal to R minus R0. Where R0 is R, so that was 37.8, wasn't it? Okay, what are we being asked then? State the type of error that causes, okay, we perform the same experiment, observe the values of S during unloading and loading are sometimes different from the corresponding values for loading. State a type of error that the differences student A observes. It's just going to be a random error. 2.3, thinner beam, same width, made of the same material. Advantage, more sag. We can say greater values of S with same loads, we should say. What does that result in if we have the same uncertainty, but we have greater values, therefore smaller percentage uncertainty in S? What's the disadvantage? Well, it's all very well as stretching it, isn't it, further, but we're actually unloading it as well. So we could say that beam could deform plastically. Therefore, well, if we're doing a graph, then we're not going to end up with a straight line. I mean, we got loading and unloading anyway, but whatever. Therefore, graph will not be linear. But that's what the mark scheme says. I don't like that because, of course, it says that it's going to be different loading and unloading. Whatever. That's what we're going to say. Certainly not going to give the same results every time, is it? 2.4, we have a graph of S against M. Okay, so this is in millimeters, though we need to be careful with that. It can be shown that S is equal to eta. Looks like an M, but it's an eta. Okay, what are we being asked? Deduce the order of magnitude of eta. Right, so therefore we have here a straight line graph and we have a gradient. The gradient is equal to delta S over delta M, or S divided by M. So rearranging this then, we can see that S over M, if you just move this to the side, S over M is equal to eta over E. This is our gradient. Therefore, eta is going to be equal to the gradient times the Young modulus. So I'm going to say the gradient is equal to, let's pick a nice point, big point, so 40, but that's times 10 to the minus 3. So I'll tell you what, I'm just going to say that that's 0.04. It needs to be meters, divided by 0.4. Oh, easy. Times by our Young modulus of 1.14 times 10 to the 9. So that's basically just 0.1 times 1.14 times 10 to the 9. And so that's going to give us 1.14 times 10 to the 8. Oh, well, we're just being asked for the order of magnitude. Okay, so therefore our answer is 10 to the 8. 2.5, we now have a different experiment with the same apparatus. Okay, but now we have log base 10 of S. People got very confused with the units of this one. S divided by M? No, it's displacement in meters, and so that confused a lot of people. They thought it was S divided by M, but yeah. I don't like the way that they do units in AQA, honestly. But that is the accepted method. But it is the widely accepted way of doing them. Anyway, whatever. Okay, what are we being asked? State what this shows about the mathematical relationship between S and L. If we have a linear relationship, you do not need to do a calculation. Well, like we saw before, if we can see that log S is equal to log L, or we can say n log L, some power, plus some log of some constant, then we can say, just going backwards, the way that we did it before, so log S is equal to log L to the power of n plus log of C. So therefore log of S is equal to a log of CL to the n. So therefore S is equal to CL to the n. Therefore we can just say that S is proportional to L to the power of some unknown constant. And that's the case for pretty much any equation ever. 2.6, when L is equal to 80 centimeters, S equals question mark, using figure 9. Okay, so L equals 80 centimeters. So we need to do the log of 0.8, and that gives us minus 0.097. So I think we can just say that that's minus 0.1, can't we? 10. And so at that point, therefore, just reading off our graph, we have log of S is equal to minus 1.53. Yeah, let's go with that. Therefore, we want S. We want to delog both sides. The opposite of log base 10, of course, is just 10. So 10 to the power of minus 1.53. And that gives us 0.0295. So yeah, I think that's okay. And then we're being asked, what is M using figure 8? Okay, so we have S. So S, now we need to read off the other graph. So S is equal to 29.5 millimeter. So reading off that, okay, fairly easy, just reading it off. 29.5, so I think that's bang on, 0.29 kilograms. I feel like I'm missing something there. Is that right? I think that's okay. 3.1, we're being given this circuit. We're being asked, what could we do to measure the internal resistance or EMF and all that jazz? Well, if we want to do internal resistance and stuff like that, then we need to, of course, add in a voltmeter across the battery to measure the terminal PD could also be there, couldn't it? But then we need to just join this up. We need an ammeter as well, and that can go either side. It seems too easy, so I understand if people struggle with that one. Bit of a weird question, that one. Okay, so we've been asked, how can we find out epsilon and R? Fine, so we are going to use voltmeter to measure terminal PD. We know that our equation is EMF is equal to IR plus IR, or epsilon, tell you what, if you call that V, epsilon is equal to V plus IR. So we change resistance of variable resistor. This changes current in circuit and in battery, of course. Therefore, plot graph of V against I, and you know that we'll end up with a negative gradient. My intercept, of course, is the EMF, and the gradient is equal to the internal resistance. EMF is equal to the y-intercept, R is equal to gradient, which is a magnitude of gradient. Let's say minus gradient, whatever. Yes, that's it. Really easy. Really nice question, that one. It's only a 4 marker, so, we don't need to go crazy. Okay, so now we have crazy circuits adding in lots of different resistors. We can see that 22 over N is equal to EMF over current minus R. Okay, we have a graph of 1 over N against 1 over I. Right, so let's actually change this up then. So let's take this equation and put 1 over N, 1 over I in there. So we have 22 times 1 over N is equal to EMF times 1 over I. Take away R. And we have a straight line graph that looks like that, don't we? So we're looking for epsilon. So therefore, we need to make sure that this is just our Y on the left-hand side. So therefore, we need to say that 1 over N, which is our Y, is equal to, we need to divide the whole thing by 22, don't we? So epsilon divided by 22 times 1 over I minus R over 22. We don't really care about that because we're just looking for epsilon. Y equals mx plus c. So therefore, our gradient is equal to epsilon over 22. Therefore, epsilon is equal to gradient times 22. So I get the gradient as 0.073 times that by 22, and we end up with 1.61 volts. There, of course, is a little bit of tolerance there because we're calculating a gradient. 3.4, we have 4 resistors connected. Show that the current in the power supply is about that. Okay, using figure 12, right. So we're just using the graph, so 1 over 4. 1 over 4 is equal to 0.25, so therefore that gets us over to a 1 over I of, reading the graph, I can see that that is 4.2, I'm going to say. Therefore, the current is going to be 1 over 4.2. We end up with a current of 0.24 amps, let's say. So there we go, our current is about 0.25. 3.5, okay, we're being asked for the PD across the power supply. That is the terminal PD. Simple. We know V is equal to IR. If we're just talking about the voltage in the circuit, that's what we're looking for. So it's just going to be 0.24 amps times, well, we have 4 22 ohm resistors in parallel, so therefore the overall resistance is going to be a quarter of that, so 22 divided by 4. And that gives us 1.32 volts, which sounds about right because we saw the EMF was 1.6, so we know it has to be slightly less than that. We're looking for R, so we know epsilon is equal to V plus IR, so therefore rearranging this, R is equal to epsilon minus V over I, so it's going to be a 1.61, let's say, take away 1.32 divided by a current of 0.24. And we end up with an internal resistance of 1.21 ohms. 3.6, okay, we got a graph of 1 against N against 1 over I again. Suggest which values of N should be used. So we need 3 more. Okay, so we want, I don't know, what are we going from? 0 to 1, 0.1 to 1. So I don't know if we go 0.25, 0.5, 0.75. Therefore, 1 divided by these 1 divided by 0.5 is 2. And 1 divided by, 0.75. Well, that doesn't make much sense, does it? It's going to have to be 1. But that wouldn't give us a very good range, would it? So no, I'm not going to say that. I'm going to say n equals 3 as well, because that'll give us 1 over 3, so 0.33. What's interesting is that they said 2, 3, not 4. They haven't said 4, they said 5, 6, or 7 for the third one. But 1 over 7 is going to give us a really, really small number. I don't fully understand that. There we go. But anyway, the idea is to ensure uniformly distributed points of data on graph. Oh, wait, sorry, they already used 1. What am I chatting? Sorry, why wouldn't they allow 4? 0.25. That's going to be better than 5 and 6 and 7. Oh, well, there we go. 3.7, finally. We're using resistors that have a resistance of 27 ohms this time. What are we being asked? Relationship is now 27 over, yeah, makes sense. Minus R. Show on figure 14 the effect on the points for N1 and N14. You do not need to do a calculation. Well, that's a little bit mean, expecting us not to do a calculation. Whatever. What did we say? We said that it's 27 times 1 over N is equal to E times 1 over I, epsilon times 1 over I minus R. And we said that's our Y, that's our X, that's our M, that's our C. Okay, so we had to divide by 27 though, didn't we? So if that's our gradient, that means that the gradient is now going to be smaller because we're dividing by 27, not 22. And how much smaller is it going to be then? 22, 5, so I don't know. It means saying don't do a calculation. You have to do a calculation in your head anyway, whatever. Just, like proper numbers. So therefore, 27 compared to 22, roughly times by 1.25. I mean, look, the point is that the gradient is going to be smaller. So if that's our line there originally, and the line should now be about there. So we know the gradient has to be 1.25 times smaller. There we go. So, not a great end to... not a great paper. I mean, it's okay. It's just some funny questions in it. As per usual, it's a paper 3A. It's not a surprise. Anyway, I hope you found that useful. If you did, please leave a like. Put a comment down below if you have any questions. Click on the card if you want to see more AQA papers. I'll see you next time.